But we realized that nobody had actually tested it directly, whether a machine learning system, given the same input as a newborn animal, would actually develop the same kinds of capacities. So that was really our opening goal going in. And I think we're going to have to start playing around with different artificial bodies, the same way we've been playing around with different artificial brains, in order to have a chance of closing this gap between animals and machines. And my hope is this tells maybe AI researchers something important about critical periods, right? So this is almost non-existent in the AI or ML world, but maybe there's something really important about learning something and then having a critical or sensitive period and shutting it down and having that serve as the foundation for the next stage of learning.
This is Brain Inspired. I'm Paul. My guest today is Justin Wood. Justin runs the Wood Lab at Indiana University, and his lab's tagline is Building Newborn Minds in Virtual Worlds. So what does that mean? Basically, what it means is Justin is comparing the very, very early development of natural organisms to artificial agents. So he does this by using controlled rearing experiments in chicks, where he controls all of their experiences, and in this case, visual experiences, because a lot of what Justin is interested in is understanding the origins of our visual intelligence and cognitive abilities from birth and through development. He controls their visual experiences by placing them, as soon as they're born, into these rearing areas in which all of the visual stimuli that's presented to the newborn chicks are controlled by the researchers. So everything they're seeing is controlled by the lab. And in tandem, Justin's lab builds models and AI agents that are trained on the same visual data as the newborn chicks. As you might imagine, this enables Justin to probe the nature versus nurture divide, or otherwise known as nativism versus empiricism. So we discussed that debate, which Justin thinks of more as a both/and kind of issue rather than an either/or issue. And using this setup, Justin has studied a number of the visual capabilities of newborn chicks, things like view invariant recognition, which is more or less the ability to recognize an object regardless of what orientation, what perspective you're taking on that object. And for each of these visual capabilities, Justin can basically build an AI model and test whether, given that same training data, the model is able to perform the tasks in the same way or in different ways, or as well as or not as well as the newborn chicks. And a lot of the early experiments that we talk about more in the episode, he was using convolutional neural networks, which is the classical object recognition network, and we talk about what he found using those. We go on to talk about, so he's taken this approach and expanded it and is beginning to study other cognitive abilities. And in the future, he'll go on to study even more cognitive abilities. But one of the lines of research that we talk about in this episode, he studied collective behavior in artificial agents and in newborn chicks, using convolutional neural networks and deep reinforcement learning and an intrinsic curiosity reward function. Okay, so the general theme here is what newborn chicks can and can't do, whether and how artificial systems can and can't do those things, and what that tells us both about the natural chicks and how to build systems that better emulate biological organisms. So it's a fun conversation. We hash all of this out and more during the discussion, and Justin's enthusiasm, you'll see, really comes through. Of course, I link to the papers that we discuss in the show notes and to Justin's lab. The show notes are at braininspired.co/podcast/173. where you can also learn how to support this show through Patreon if you value what I do here. You can send me enough to buy a cup of coffee every month, or you can send me a little bit more and get the full episodes, and or even join the Discord community, which is filled with like-minded listeners like you. One last announcement here. I'll be in Berlin, Germany in late September as part of a workshop that's associated with the Bernstein conference in Berlin, Germany. That's actually September 26th and 27th. The title of the workshop is How Can Machine Learning Be Used to Generate Insights and Theories in Neuroscience? And actually, Justin would be a great person to participate in that workshop. He's not going to be there, but There'll be a lot of great researchers that are there who are going to give talks. And then at the end of this 2-day workshop, I'll be moderating a panel with a handful of those researchers and discussing how can machine learning be used to generate insights and theories in neuroscience. So if you want to learn more about that, I'll link to that in these show notes. Again, that's braininspired.co/podcast/173. You should register for that workshop. It's going to be a lot of fun. It's going to be very interactive, and you should come say hi to me if you do. That'd be fun. Okay, thanks for listening and or watching. Here's Justin. Justin, you are studying bird brains these days, bird and artificial bird brains these days. And we're going to talk all about your controlled rearing studies and what you've found out with regard to natural and artificial intelligences. But I kind of want to go back to the beginning and ask how you came to, so I will have introduced a little bit the ideas of, what you study in the introduction, but what led you to this point of raising these chicks in highly restricted virtual environments to compare them with artificial networks?
Yeah, absolutely. So it's been a winding path. So I actually started in graduate school working with young human babies. So I always loved the origins questions. I always wanted to know, what are the core drivers of cognition and perception and action, right? What are the learning algorithms in newborn brains that make it possible to learn object perception and navigation and make decisions and do all of the amazing, wonderful things that humans and animals do. And so I've kind of moved from population to population in an attempt to try to get at those questions. So I started with 5 and 6 month old babies when I was in graduate school. And that, of course, got me introduced to this idea of looking at what might be present in a young human brain. I started to realize that, and this will come up later when we talk about chicks, I believe, but I started to realize that even though we were using young human infants, that's not the way to get at the nativism empiricism question, because, of course, anything you find in a 5-month-old or a 1-month-old or even a 1-week-old could, in principle, be learned, right? So it becomes incredibly difficult to distinguish between nativism and empiricism perspectives, right? Do we start out with something like a domain general transformer, for example, when we're trying to model the brain, or do we really need to build in a collection of domain-specific core knowledge systems, for example? And that's how I was trained in graduate school. And so that's basically I see that as one of the major debates in the field. It, of course, goes back thousands of years to Aristotle and Plato, but we haven't really been able to get at it directly, right? And so I'll go into why chicks is what I believe the only model system we can make a run at those questions with. So anyway, yeah. So I went to babies. I then went to wild monkeys for several years. So this was partly to escape cold Boston winters, but it was an absolutely wonderful experience to go and work with wild monkeys. And I basically just compared what are the perceptual and action perception abilities of monkeys and how do they compare with those of young babies. And so I spent several years doing that, kind of trying to find commonalities between the capacities of non-human animals. And given that monkeys lack culture and language and all these uniquely human trappings, it was an interesting way to look for dissociations between particular cognitive capacities and culture, language, and so on. So I did that for several years. And then when I started up my own lab, I dove straight into newborn chicks. So during I'll pause for a second. Yeah.
Well, yeah, but so did you just have an epiphany that you needed to study the chicks, or was this always eating at you, this nativism, empiricism debate, and how maybe the wild monkeys that you were studying and the human infants, just you couldn't really get to what you wanted to study? Did you have an epiphany over a coffee one day, or had this been the idea for a long time, the chicks?
Yeah, great question. It actually started, I remember exactly when it started. It was with my first meeting with one of my graduate advisors, Elizabeth Spelke. And I remember sitting across from her and mentioning that these were the questions I absolutely cared about. And we just started talking about chick research. And she then inundated researchers in the lab and grad students in the lab with, this is, perhaps the one model system we can use because we can control everything they do from the very moment of hatching, control their experience, and then see what are the causal roles of experience in terms of shaping perception, cognition, and action. So I had wanted to do it from the very beginning of graduate school. And then when I finally had the freedom with my own lab to do so, I basically just started figuring out, how do we study newborn chicks precisely? That was really the kind of the big gap in the field, is that there had been studies with newborn chicks for, really for decades. But the data had a low signal to noise ratio. And this is kind of one thing coming up in the reverse engineering enterprise is you really need high quality data to ask, does my machine that I just grew in a virtual environment, does that actually map onto one of the target systems that I care about, namely an individual chick? And if your individual chicks are across the board in terms of the measurement space, then you might have a model that performs at chance levels and it'll still match up to one of those chicks, right? So you can't have a huge amount of variation in your target population if you really want to try to do this direct mapping between how does an animal learn and how does a machine learn. So the first 5 years of my career were really spent just trying to figure out how to automate the whole process. So, making it so we could record 24/7. We could give newborn animals thousands of trials that lasted, 20 minutes at a time or 40 minutes at a time, and really collect these detailed measurements of how newborn animals are learning as a function of particular experiences. And then once we did that part, we then had the data that we needed in order to start reverse engineering. And so that started to happen around 2015, 2016, when we really jumped into the AI world.
Okay, that was going to be my next question also, but maybe even before that. So I'd love for you to just describe the process on the natural side, from from the chicken, I don't know if it's from hatching, and like just what happens from that point, to them living in these, incubators in these systems of these virtual worlds. But before that, do we like chicks because as they're developing in the egg, so if a human in the womb can be said to be learning in the womb because it hears mom's voice, singing songs and, yelling at dad and stuff. But chicks, is it just that, they have less and less opportunity to quote unquote learn in the egg relative to mammals in the womb, et cetera?
That's I would say that's part of it, right? We have more access to their prenatal development. So if it does turn out, and this is one of our working hypotheses in the lab, if it does turn out that prenatal training data really matters for building a brain so that it then reveals, so to speak, innate knowledge at the birth state or the hatching state, then we really need to be able to study that prenatal developmental process. And ideally, of course, put AI through the same kind of training data, right? So this is one thing we're doing in the lab is we're training artificial neural networks with retinal waves and other kinds of prenatal experiences that we think occur prenatally. And then we can ask, if you have been trained on retinal waves and muscle twitches and all the things happening to an animal prenatally, do you end up with something that seems a little bit closer to how biological intelligence works in the newborn state than what we currently have with machines? And I really think we're going to need to dig into that prenatal state in order to be able to tackle it. But that's not actually the reason we switched to chicks. The main reason we switched to chicks is they're the only animal in the world, at least to my knowledge, that you can raise in virtual reality. And you might ask, of course, fully 24/7 in virtual reality, right? So we hatch chicks in darkness. We then put on night vision goggles when they're hatching. And then we move the animals in complete darkness from their incubator over to their controlled rearing chambers, these virtual reality chambers. And then we flip on the chambers and thereby giving us full control over everything they see, right? So every object they see.
Super naive question though. I don't even know with chicks, do moms lay on the eggs for a while? Do the hens lay on when do you start handling it? And this doesn't matter probably.
No, it might matter. We don't know what matters. That's one thing. That's kind of one of the main mottos of the lab is we don't know what matters, right? In terms of the models, in terms of the environment, in terms of the experience. So it's all open. We just need to be empirical about it. But yeah, in the wild, a mother hen will roll the egg once in a while, so they'll turn the egg so that it ends up developing correctly. We use an automated incubator to do that, so it basically just rotates the eggs every 45 minutes, and so it basically replicates the kind of rearing conditions that animals are getting in the wild. And then, of course, once the virtual reality part starts, then it's a very different kind of experience than what they get in the wild.
Yeah. Okay. All right. So you bring them over in darkness with the night goggles on. You place them in the virtual environment, and then what happens? Then what's the setup?
Yeah, and then so we basically just let them do what they will do. So we program the virtual world. So We rely on imprinting, at least in our early experiments. So imprinting, I imagine much of your audience might be aware of this, but imprinting is basically just an early social preference that you develop in life. So it's fetal imprinting is the most well known of this, just because it was studied, noticed back in the in the 1500s, I think was the first observation of imprinting. People would notice that baby birds would very quickly develop a preference for a caregiver. And of course, Konrad Lorenz really popularized this, as we see those wonderful photos of little geese following after Konrad Lorenz as he treks down a river. And so, this has been a well-known phenomenon for a while. And so it ends up being quite convenient for us because we can essentially just put a virtual object in the chamber. So our chambers are essentially just white walls, except for 2 of the walls right now are LCD monitors. So we can import whatever kind of virtual stimuli we want into those virtual chambers. Maybe you want to raise an animal with a single object, for example, and maybe that single object is only seen from a single viewpoint range. So we can essentially vary the experiences that the animal gets, and they'll imprint to that, whatever that might happen to be. And then we can change around the characteristics of that object and see if they think that it's still mom. Right. So I know that this is mostly auditory, but so I always like to look for props. But I imagine like holding a coffee cup, and you only get to see that coffee cup from one perspective. And the chick imprints to that coffee cup from one perspective. What if you then show them the coffee cup from a different perspective that produces a different image on their eyeball? Will they still recognize that object? So this is known as view invariant object recognition. You can also do this with things like background invariant recognition, right? You can put an object on a background, and you can see if the chicks can recognize that object across a different background. So we essentially went through dozens, hundreds of experiments asking, how rapidly and quickly does high-level vision emerge in newborn chicks? So what do they need? What kinds of experiences do they need to develop view invariant recognition and background invariant recognition and the ability to bind colors and shapes into integrated representations in memory, and things like object permanence and action recognition? Those are kind of the main capacities we've been looking at so far. And I think, what's really surprised me, at least, is how little chicks need to learn these high-level abilities. So even a single snapshot of an object, right, just a single object just being flashed over and over again from one viewpoint is sufficient for a newborn animal to be able to recognize that object across a wide variety of other viewpoints. Which at the beginning almost seemed like magic to me, right? Like, how on earth would an animal be able to recognize a 3-dimensional object, having seen no other objects in their lifetime from other viewpoints? How might that capacity emerge? And so that, of course, is where the AI comes in, is because it can actually give you an answer to that question if it turns out that the AI system's doing the same thing that the chick is doing. It takes us beyond nativism magic, so to speak, right? This has always been a problem, is you can say something's innate, but the explanation was always a little bit like magic, right? Like, well, it exists. We have no idea how or no idea why, but that ability exists in the newborn state. So we're really trying to figure out mechanistically why that's the case.
So you said you were surprised, but what did you think would have happened? I mean, because you had already studied the innate or the cognitive skills of newborns for a long time. What did it really surprise you, or was that your hypothesis going in?
It actually really surprised me, and I think I had been influenced by machine learning experiments, right? So these were these experiments where you dump in tons and tons of data, of course, into CNNs or transformers, and you find that typically they needed, or this was at least the wisdom back then, is you needed a huge amount of data, right? A huge visual diet in order to start breaking into this problem of recognizing objects from different viewpoints. Given that was the one learning system that existed that was actually replicating this capacity of view invariant and background invariant recognition, that was my starting point as a hypothesis, is maybe chicks are something like these machine learning systems. Maybe in the first couple of days of life, you still could see, in principle, hundreds of objects wandering around the natural world as you see mom, mother hen, and you see mother hen moving across backgrounds, and you see her from a whole bunch of different viewpoints, and then you see your grazing field in the barn, right? Within one day, you could acquire a massive amount of experience about the world. And so I thought that maybe that massive amount of experience might be necessary or might be required, and as it turns out, it's not, right? It just requires this little bit of data, and from that little bit of data, you end up getting these high level abilities emerging.
See, I kind of had it in my mind because you had done a bunch of these studies in the early 2010s, right? And I suppose a little bit before that as well, maybe. I had it in mind that you had the idea of how the newborns would acquire these skills, and then kind of with the rise of convolutional neural networks and these artificial intelligent networks, then you thought, oh, well, now I have something to compare it to, but maybe I have it backwards. Did you have the models in mind and when you were developing the experiments?
Yeah, they really kind of happen side by side with one another. I mean, so, back when we started this work with chicks, it was 2010, which is of course before AlexNet. And so the computer vision systems on the market weren't nearly as sophisticated as they were. But I still remember some early James DiCarlo papers, especially one that he wrote with David Cox. It was a Trends in Cognitive Science paper called Untangling Object Recognition. And I remember reading that paper like 10 times, just trying to transform my brain from more of a nativist way of thinking, that just something is there, but no understanding of the mechanisms. And I just remember reading that paper over and over and just trying to understand what it means to think about the brain mechanistically as a series of transformations across a series of layers. And that paper just completely transformed the direction or the arc of my research. And then I got very interested in AI. I was, of course, quite excited when AlexNet came out, and then just kind of waiting with bated breath until an unsupervised model would come out, because, of course, chicks don't learn through supervised learning. So we needed to wait till things like SimClear and then these other unsupervised models came out till we could really make that detailed comparison. But yeah, a lot of my career has just been waiting around for AI to come up with an algorithm that would somehow learn in an unsupervised manner. And, that happened about 2020 with SimClear. And now transformers, I think, are the next stage of that, right? They're these kind of full-blown embodied models that can handle high-dimensional action spaces and have very few inductive biases and nevertheless can learn these amazing capacities. So yeah, it's quite fun right now, especially with AI providing the models that we then plug into the artificial animals and see, does the transformer, does the CNN actually end up learning like the actual animal itself?
Yeah. Oh, okay. Well, so the first AI models comparisons that you made, as far as I know, were with convolutional neural networks, and you tested different types out. But then you've gone on to look at, and we'll talk about all this, to look at collective behavior, and in that you implemented the same kind of convolutional neural network, but also as a model, but also a reinforcement learning agent with curiosity and intrinsic motivation. And so, are you transitioning to transformers now? It's like the latest and greatest. You just plug it in, and
absolutely, yeah. The transformers, I think, are fascinating, especially from for many reasons, but especially from a developmental psychology point of view, because they have such minimal inductive biases. And this has always been the debate, right? Is do you need strong inductive biases to make learning possible? And nativists have kind of come into the game with this, I think, strong assumption that training data is like sparse, noisy, and impoverished. You'll see this all over the place, right? Going all the way back to William James is this basic assumption that the training data, the proximal images we receive, just aren't good enough for learning. But I think AI is giving us a completely different story of this, right? So, for example, transformers, if you do things like masking procedures, you can mask out 90% of the content, and yet that's when these models learn the best. And so what that tells us is that these models that the training data is highly redundant, it's highly structured. And so if you have a powerful enough domain general learning mechanism, at least in principle, it's possible to be able to leverage that structure and redundancy in the data to be able to learn a good visual model of the world. Maybe like what objects are and how to, what the world is like, what space is like, so you can navigate in all these, of course, critical capacities we need to learn. So, transformers, I kind of said differently, are, I think, a good scientific model because they're so relaxed in terms of their inductive biases. And they let us test this very strong extreme hypothesis, which is that maybe most or all of intelligence emerges from a domain general system, right? This would have been an empiricist. This is what empiricists have been arguing for a while. It lets us test that very, very strong hypothesis. But to be fair to nativists, I want to say I'm agnostic about nativism versus empiricism.
Oh, I was about that. That'd be my next question. But how did you used to be more nativist, and now you're in the where? Like, how did that evolve?
I've switched back and forth like 5 times in my career. So, and I've realized the reason why is because nativists and empiricists often look at different evidence in order to support their theories. So I kind of got to
Of
be
course.
trained by nativists at one point during graduate school, and now I'm at Indiana, by Spelke and Carey, and now I'm at Indiana University with Linda Smith and a whole bunch of wonderful people here who are kind of more on the empiricist side of things. And it just seems really clear they're just picking at, they just pick different kinds of phenomenon to support their claims. And this is fine, of course, but I actually think both ideas are going to be right. And so let me just kind of specify that just so I don't, nobody comes away thinking I'm an empiricist or a nativist. I really think both ideas are right? So you could have a single domain general mechanism and that might be something like the starting point at prenatal development. But you might imagine that prenatal training data is so rich with these retinal waves that are very object-like and have these important second-order correlations, just like natural data. You might imagine that at the birth state, you really do have something like core knowledge, right? I mean, and then that would mean the nativists on some level were right to suggest that at the birth state or the hatching state, you would see something like object knowledge, like object permanence or view invariant recognition or the capacity to navigate and take novel paths between places. So I really think the idea of core knowledge phenomenon might be right if we take training data seriously during prenatal development. So in a way, we've got the nativist being right because maybe core knowledge does exist. It is present. It is a phenomenon in the first maybe days or weeks of life. But that might all emerge from a domain general mechanism, which would make the empiricist right? So this is kind of my hope of getting past this debate is we want to build a test bed where people can just test it one way or the other. So this is what we're doing with all of our chick work is essentially trying to build a public test bed where researchers around the world can just plug their brains into our artificial chicks, whether they're a nativist, whether it's a nativist theory or an empiricist theory, and just run the model across the range of experiments that we've done and see if it's a good match, right? And then we can just test a bunch of nativist theories, we can test a bunch of empiricist theories, and we can see which one ends up being the best match for what chicks are actually doing. So I love this idea in computer science of making public benchmarks so everybody can plug in their models. So, a grad student has exactly the same chance of coming up with the right model as a full professor, right? That's how it should be, I think, in a good science. So
right. Yeah. But so the we haven't really talked about how your experimental setup is like fully automated and why that's an important thing. And I know that you worked really hard on the technical side to get all this right, and now you have how many rigs? 30,000? How many do you have? Like what? 20? Something like 20? Or
we had 60 rigs back at USC.
60.
Yeah. So this was we could run about 8 experiments at a time. Each with multiple subjects in it, and we were able to collect a massive amount of data very quickly. And critically, it wasn't just a lot of data; it was also very precise data. So we can make precise predictions for each individual subject rather than relying on inferential statistics. And we can maybe come back to this. I think there's right now, I think there's a lot of interest in bringing psychology into the AI world, but psychologists have largely relied on inferential uncertainty, whereas researchers in AI care about predictivity, how well you can predict things. And those are completely different from one another. And you can show that you might have the smallest p-value you could ever want to get something published, but it doesn't produce the kind of benchmarks you need for machine learning, right? That the data might be too variable to actually serve as a good benchmark. So that was really again, the first step of automation is how can we get a good benchmark so that the cloud of dots representing the individual chicks is actually separate across conditions. So it's really easy to see if your machine is more like one or more like the other.
Okay, should we talk a little bit about the early convolutional neural network experiments? And this is kind of serves as background for the rest of your experiments. And it sounds also like you'll have experiments for the next 100 or so years lined up because there's so much that you can do.
That's the hope. And the hope is, we're building these new VR chambers too. So this might come at the end, but we're building these new VR chambers that are full on VR. So we have a camera that basically monitors the chick as they're moving, and they're surrounded by all 4 screens, almost like the cave, the human cave VR system, where you move around and the walls update. So we built this for chicks. Wonderful graduate student in my lab named Joshua McGraw is working on this. And it essentially allows us to raise chicks in any kind of world you can imagine, right? So a world where object permanence is true or false, or a world where objects don't obey their boundedness or their shape as they move through time and space. So you can really give animals these kinds of strange, unnatural experiences and really kind of make a run at these questions. Is it built-in knowledge of object permanence, for example, or is it learned based on seeing objects disappear and reappear from view?
Yeah. Okay. Well, Yeah, let's start with those convolutional neural network experiments, and maybe I don't know if you want to end up. I won't. Well, before that, actually, you had shown that there are two properties that are really important for chicks to learn things like object invariance, and that is that the objects that you're showing them need to vary smoothly and slowly, which is quite interesting. And I think we'll keep coming back to this nativist versus empiricist sheen because I have a bunch of questions like, well, what does that mean early on, and so anyway, but if the objects are moving fast and if they're like kind of jutting around so that you don't get a smooth transition, then the chicks don't learn the objects as you're showing them.
That's exactly right. Yeah. So, 10 minutes ago, I mentioned all of the amazing capacities of chicks, right? So from a very little bit of training data, they can do a whole bunch, right? They can recognize objects across novel views and backgrounds and so on. But as it turns out, the way that they do that is through heavy constraints on learning. And these two heavy constraints appear to be slowness and smoothness. So if an object is not moving, slowly over time, then essentially what the chick builds is this kind of, it's like an abnormal object representation in which action information is part of the shape representation. So they really care about how that object moved. They don't particularly care about what that object is. And what I really loved about these experiments is you can basically causally manipulate the first representation an animal makes. So if you make the object move slowly, they build these beautiful view invariant representations. If you speed up the object a little bit, all of a sudden you start pushing it into an action representation. And so, this to my knowledge was kind of the first way where we had like strict causal control of manipulate this experience, and it will directly impact the nature of the visual perception that emerges in the animal. So this is really exciting because these are the kinds of constraints I think we need to really understand what's under the hood, right? So we should expect whatever the learning algorithm is to show these same constraints. A machine should be subject to the slowness and smoothness constraints the same way that a newborn chick should, if we've really figured it out, right? And if we haven't figured it out, which we haven't yet, then we know that we have the wrong models, right? We know that there's some other model out there that leverages time to a greater extent than current ML systems do, and perhaps those should be the next systems we test. Yeah.
So you want those constraints in a system that you're building in order to learn about how we do it or how brains do it. But if you're building thinking about those constraints, it is potentially limiting, and maybe that's the price we pay for whatever quote unquote general intelligence that we have. Is like we have these very narrow constraints, right? Like we only see a very narrow band of UV or of electromagnetic radiation and of light, in other words. So how does that make you think about our own intelligence? I know this is kind of a big question before we get into some of the details, but do you think that does it make you think we're more narrowly intelligent, or is that's something necessary for our wonderful general intelligence? This constraint of smoothness and slowness, and we can't keep track of things that are moving really fast, that sort of thing.
It's a great question. I mean, the natural world is slow and smooth. So for every animal not born in our lab, they're good to go, right? They'll have all the right kind of training data they need. They'll get, if you look around the room, most things aren't moving at all, right? So that's what I mean by slowness. And when something does move, it tends to attract your attention. You fixate on it, and then it's slow in terms of the proximal images hitting your eyeball because you're actually following that object as it moves. So, I think the natural world essentially provides all, meets those constraints we need for high-level learning. So, I don't really think about the brain as being highly constrained because of those unnatural constraints, so to speak. Why we like those constraints, is because they give us ways of distinguishing between candidate models, right? So the fact that it's learned, the fact that experience seems to play a causal role in developing view invariant shape representations, in other words, suggests that that's not hard-coded into the brain, right? Chicks probably don't come into the world with some sort of notion about what three-dimensional objects look like. Rather, our speculation is, chicks come into the world with something like a domain general learner, and the world is filled with objects. And as long as those objects move in the right way, which is slow and smooth, perhaps it needs to be that way because of, temporal windows and spike timing dependent plasticity. We don't know at this point, but that's our kind of working hypothesis. As long as you have those basic requirements, then you can see learning happening pretty rapidly.
I don't know anything about chick saccades, rapid eye movements, like ballistic eye movements, because the slow and smoothness is not doesn't jibe well with the way that humans and other primates move their eyes. And like every time you move your eyes, you have kind of a completely different scene, which is not smooth. But the object itself might be moving smoothly, but your perception from your eyes, from your vision, is not. And so we have to like compensate for that. I don't know if you've. I just thought, I have a background in saccades, so this I have to think about this.
Oh yeah, no, it's a great point. And actually, James DiCarlo has done some wonderful work on this. So he did work with I think this is 2008. The first author was Lee. But basically, they put monkeys in a natural world where when the monkey saccaded, you would change something from like a tiger to a teacup. And what they found is that in IT, you start seeing those tiger and teacup representations coming closer and closer together, as long as they're part of the same kind of temporal. They have that temporal continuity. So I think this still works even with animals that make extensive eye movements. Chickens, they have a little bit of eye movements, but mostly they just move their head instead of their eyes in order to refresh their retinal image. But I think the same general principles, right? That's ultimately what we're chasing, is these general principles of learning. I think those seem to be true from what we can tell across chicks and across monkeys. There's also some really nice work by Linda Smith where she looked at young children. You put a camera on a child's head and you ask, what kind of data does that child acquire? And one of my favorite findings that she has is that babies or toddlers make object data really slow and smooth. So they'll pick up an object and they'll hold it completely still, and they'll still their head too, and essentially making it so the retinal images going into their brain are very slow and smooth. And when they rotate it, they'll rotate it again very consistently and very slowly, especially focusing on planar views. So even if we just look at the natural behavior of young children as they're learning, they're actually spontaneously making data slow and smooth, suggesting that maybe this really is a deep principle about visual learning, and maybe learning more generally is that you need slowness and smoothness, maybe allowing the temporal machinery of our brain to link up these time slices in the world into coherent representations.
Okay, so you raise chicks in this virtual world, and you're showing them one object, you're imprinting them with one object, and then you test whether they're imprinted by showing that same object on one side and a different object on the other side, and how much time they spend among these different objects is an indicator of whether the imprinting worked and whether they have this type of, whatever you're testing, object view invariance, etc. And then you train a convolutional neural network. You take different types of convolutional neural networks that have either been super massively trained on ImageNet with thousands and thousands of images to learn how to categorize those objects, and a few different kinds of convolutional neural networks. Could you just kind of talk us through that, and then tell us what you found? And these are kind of the early AI experiments, right?
Yeah, absolutely. And we actually have a paper that I think the paper I sent you is an Archive 2021 paper. So we have a new paper working on that's basically fleshing all of this out, looking at different architecture sizes. But basically, kind of long story short, is that the goal of it was to ask, can we build an image computable model of a newborn visual system? And if we can then test, is it the case that machine learning systems really are more data hungry than newborn brains, right? You see this claim everywhere. So it used to be everywhere with CNNs, is that, well, CNNs might be good models of the brain, but we know they're trained on 14 million images from ImageNet. Yeah. That's radically different than the visual diet of a young child. Therefore, these aren't the same learning systems. But we realized that nobody had actually tested it directly, whether a machine learning system, given the same input as a newborn animal, would actually develop the same kinds of capacities. So that was really our opening goal going in. So what we did is we essentially, you can't put a camera on a chick's head. They're too heavy. We actually tried this and it didn't work. But what you can do is you can simulate the visual experiences of a chick in a video game engine. So you can essentially just yoke the camera in a video game engine to the head of the chick. And then you can just move the agent. You can just basically move the camera with the chick's movement and then collect all the same visual images that the chick gets. And so, we've done kind of versions of this with kind of more simple base agents. And what we find is that that's enough. Like the kinds of massive data augmentation that you get when you get to look around the world and move around and select your own viewpoints, that ends up being kind of the key missing piece necessary to build view invariant recognition. So kind of said differently, even if you have a single object, I can move farther away from that object. I can get really close to that object. I can look at it from the sides, right? I can augment, I can do natural data augmentation the same way that engineers do, artificial data augmentation like color jitters and swapping. But an animal can actually augment their data however they want. And so if you give CNNs that same kind of augmented data from the environments of the chicks, they end up solving these view invariant problems. So that was really the goal, is to try to match the training data as closely as possible between the animals and the machines. Because if you don't match the training data, you have no idea what the problem is if there's a gap, right? So it might be like, let's say a machine and a human are doing something different from one another. Well, one possibility is that maybe it's the learning algorithm that's different. But another possibility is maybe it's the training data, right? You have no way of knowing if it's the learning algorithm or the training data that's leading to differences. So if you clamp down on training data, you can now make an inference that if two things are different, it's likely, either the body of the system or the learning algorithm of the system. And of course, those should probably be treated as the same thing, right? A brain's in a body, and it's a single learning system. So that was really our goal there. And then we recently did, grad student in my lab, Lalit Pandey, recently did this with transformers, where we thought, maybe CNNs with their kind of beautiful hierarchical structure would be able to learn from sparse data, but no way with transformers, right? They just don't have the inductive biases to be able to do this. And as it turns out, they perform a little worse than chicks, maybe 5 to 6% worse, or than CNNs, maybe 5 to 6% worse than CNNs, but they still solve the task. So you can start with the most minimal inductive bias we have in ML, in machine learning, and you can just give it limited training data of a single object from a limited viewpoint range, and transformers will learn view invariant representations. So I think this is really important because even transformers don't appear to be more data hungry than newborn visual systems, right? This argument that you see in every popular media story and almost every scientific paper about the data hungriness of these systems. I mean, we've just run one study so far, but it looks like, from what we can tell, when you really equate their training data, it's not actually clear that one's more data hungry than the other.
Well, one of the interesting things about the CNN studies, and you can tell me if this is true of the transformers as well, I had mentioned that you tested it against also a CNN that was fully trained on ImageNet. And it turned out that CNN performed better than chicks, and higher, was more accurate for object recognition of view invariance than the chicks, and also more accurate than the CNNs that were trained just on the virtual world chick data. But the issue is that the CNNs that were trained just on the chick data actually matched the chicks' behavior better. It was a better indicator of their actual cognitive ability.
Exactly. And so I think kind of what you're suggesting is maybe, we see this really as a closed loop system, right? So you're never done just when you show that the CNN matches the chick. The next experiment, of course, is then to, put chicks in a more natural environment, something a little bit, well, you can't do anything like ImageNet, but a much more natural environment. Maybe you have dozens of objects virtually around the animal. Maybe they're 3D, so they change perspective as the animal moves. And then you can ask, how does that more fully trained chick compare to a CNN that's been trained on that data, right? So you can continuously cycle around asking, given that the animal required this amount of training data, the same should be true of the machine. And then you can, for example, generate new predictions with the machine and ask, does the animal actually match those predictions that you just generated from your model, from your machine? And you continuously go around the cycle until you close the gap between the animals and the machines. So, I really don't think this is sort of the end point. I really see it as the starting point of now we have a closed loop system where animals and machines are connected with one another. There's no human in the loop deciding what counts and what doesn't, what phenomenon we should care about and what we shouldn't. It's just a completely automated system. And so now we can just basically go around this closed loop system over the next, hopefully several years, and gradually close the gap in vision and navigation and other areas that we look at.
So do you have versions of transformers that were fully trained that also outperformed the transformers that you trained in a more realistic way? Or?
So we've mostly stepped away from ImageNet trained systems in our newer papers, just because it's not I mean, it's interesting for an
You're
AI
done with
audience.
it.
Yeah, yeah, right. I mean, it's like ImageNet is such a weird visual diet anyway, right? So like snapshots from many of your prior guests have made this claim. So, but right, it's such a weird visual diet to get, because you don't actually get to do what a child does, which is, pick at that object and look at it closely and move it around or interact with that thing. And so we typically don't use ImageNet trained systems. We just train them from scratch. So we'll just take an untrained system, give it the same training data as a chick that's been simulated. Where a new project is actually, first we'll train it on retinal waves, and then we'll train it on the visual diet of the chicks. So to ask if retinal waves give you an extra bump in performance, so to speak. But yeah, we're really just focusing on matching the training data at this point.
So if you can get the same performance from a CNN and from a transformer, is it just that cognition is just so multiply realizable that we're going to be able to simulate visual development in 12 different ways? What does it tell us?
Yeah. So I think I think the field is discovering the answer to that question right now. I certainly don't have an answer. I can speculate, which is that, of course, like anyone, but I think that there's something about this direct fit idea. So this is something that came up from Mita-san at Princeton that I think you interviewed a couple years ago. This idea that maybe what brains are doing, and we know that ML systems are doing this, but maybe what brains are doing is they're just fitting to the space-time features of embodied data streams, right? So maybe they're just very, very flexible and they fit to those data distributions. This might happen in a purely unsupervised way, like predict what's going to happen next, like NLP systems or masked autoencoders. But maybe just that fitting process is what we see during development. And if that's the case, if it's just kind of a large scale fitting process, then that shows us that it's not just that it's kind of multiple. I mean, it suggests that as long as a system is fitting, whether it's brain or whether it's silicon, but as long as it's fitting with a lot of parameters, then we should perhaps see the same kinds of capacities emerging, right? So another way of saying this is like, we want to push the animals and the machines to the same part of this parameter space. And maybe that part of the parameter space that you push towards is fitting to the fitting to the underlying data distribution. In which case, the prediction I think we would see is that that's a general principle of learning. And as long as you make a system fit to the underlying data distribution through something as simple as prediction or masking or auto masking, we should see these capacities emerging. So that would be my speculation, is that there's something really deeply right about fitting to underlying data distributions. And given that we have 86 billion neurons connected to another 1,000 to 10,000 neurons, that's a lot of dials you can turn and tweak in order to fit to a high dimensional data distribution. So that's kind of my working hypothesis about what's likely underlying vision. But of course, it's just a guess, but it's empirically testable, right? That's what transformers do, especially these ones that fit, is we can see if that's actually enough, right?
How many neurons does a chick have?
How many neurons does a chick have? Several million. So it's a smaller system than humans, nicely. I think humans are quite complex and take a while to develop. But they have all the same kinds of cortical circuits and large-scale brain architectures as mammals. So there's this old kind of myth that bird brains are radically different than mammal brains. This comes from early observations in the 1950s, where researchers with very low precision techniques went into the brains of mammals and birds and noticed, wow, nuclear versus layered organization, they look totally different. Therefore, birds and mammals must be thinking in really different ways. But the last 70, 80 years has shown us that that's wrong, right? I mean, the cortical circuits are almost identical in terms of their input-output connections. They're produced by homologous genes. Our common ancestor was only 300 million years ago, and you can see that canonical cortical circuit in both birds and mammals today. And you even see the same like large-scale hub organization with prefrontal and hippocampal and visual areas. And so I think that especially as we're comparing animals to machines, I think the distance between birds and mammals is actually quite small. And given that you can't raise mammals particularly well in VR 24/7, if you can do it at all, I think birds might be the one chance we've got as scientists, at least to make a run at these questions of nativism versus empiricism.
You mean birds and mammals is really small relative to birds and AI models?
Exactly.
Is that what?
Exactly.
Okay. Yeah.
Yeah, that's what I
So
meant.
you had
Exactly.
mentioned,
So,
yeah, okay. Go ahead. Sorry, go ahead.
Oh, no, I just was clarifying that's exactly right. Yeah, is that, we often
Oh,
make these comparisons between primates and CNNs or primates and transformers, and yet a lot of researchers are a little bit reluctant to go to birds because primates have often been the model system for object recognition. And so,
right.
this is often the field kind of getting into an attractor basin that might not necessarily be entirely healthy or might be pushing us to become too specific in terms of what we're studying. My suggestion would be we need to relax that attractor basin a little bit so that we can study other animals that might give us other advantages that primates don't give us. So you can't raise a monkey in VR
Yeah.
from birth, and yet you can do this with a chick and really push around and see what the role that experience plays in developing knowledge.
Well, so I was going to ask about, and we don't have to perseverate on this, but I mean, you had mentioned that mammals develop their visual system and visual intelligence develops more slowly, takes more time to mature. And I don't know if do birds have a critical visual period like mammals do early on, and or there's this whole pruning effect. There's the brain is developing, making thousands, millions of connections per day or whatever in the first few weeks, and then there's this pruning back, and that's part of the process as well. And I don't know if that has. Do you think about that, or is that an issue with chicks, or do they not have such a pruning, and do they come out a little bit more hardwired?
They come out a little bit more hardwired. Um, I it could still be coming from a domain general mechanism, that hardwiredness, right? Because you could imagine
Right,
domain
right.
general through prenatal training data. Yeah. So I just want to clarify, there's a difference between kind of learning something and then having it being there at the birth state versus genes actually hardwiring the thing into the system per se. And those are kind of two different
Yep.
versions of nativism. So I just thought it'd be worth distinguishing between those. So chicks are basically ready to go right away. So about 48 hours after birth is when they reach their peak visual acuity. It's much lower than humans. So human visual acuity is about 35 cycles per second. Or 35 cycles, and chicks is about 1.5, which is better than rats and better than mice, but certainly not what you get at with what you get to with humans. So there's a lot of differences, or there are some differences. It just, we don't know how much these matter, right? This is the problem with reverse engineering, or the fun of reverse engineering, depending on your perspective, is it's kind of more of an art than a science, right? So you start simple and you take a guess of what matters, right? Maybe CNNs matter, maybe transformers, maybe RL, and you push that system as far as you can get, and then at some point it's going to break and you're going to notice differences between the animals and the machines, and then you just start plugging other stuff in, but critically you start simple, but then you plug stuff in when you need it, and then you can ask, what is that extra thing that I just plugged in? What does it gain me in terms of function? And I think the ventral visual stream is a wonderful example of how this research program has emerged, right? I mean, Dan Yeamans and DeCarlo started with just feed-forward systems, even though they perfectly
Right.
knew well that there's huge recurrent connections. But there was a lot of value to knowing that a feed-forward system could actually solve many of these hard problems of vision. I remember back, 10 years ago, 15 years ago, when I would teach vision classes, I had this slide that said, we have no idea how vision works, right? It was a little bit mysterious. We didn't know, generally what kind of system you needed to solve it. And now, of course, I have a whole lecture on how vision works and how we can replicate it with feed forward and also recurrent neural networks and what you gain by adding in each one of these extra little pieces. And I think that's what's really beautiful about reverse engineering. It's not that you just throw the most complicated system you can at it at the beginning. You really just start small, see what you can get with, for example, reinforcement learning and CNNs in the case of collective behavior, see how far you can push that, and then start adding in more complex models as you need them.
Well, speaking of starting simple, what do you say to people who, so the original experiments that you did comparing neural nets and brains involved, just a blank screen, a single object for, I don't know, days and days maybe. I'm not sure how long it lasted, the training. But that's a far cry from a naturalistic, ecologically valid environment. And right now, there's this huge push that we need to get beyond these sort of task-defined and minimalistic toy models, et cetera, toy experimental setups, and because it doesn't necessarily apply to the naturalistic, ecologically valid world. But I know that you're moving more and more toward that with the virtual reality systems and what we're about to talk about with the reinforcement learning, et cetera. But how do what's your response to that kind of feedback.
Yeah, I would say that's absolutely right. But it's important to distinguish between two types of naturalism, right? So on one hand, we can talk about the naturalism of the images, right? So in this case, something like ImageNet, right? You're showing natural images. These are images that were taken from the natural world. So on one hand, you could talk about the naturalism of the stimuli per se, but on the other hand,
Right.
you could talk about the naturalism of the data that can be acquired by the model. Right. And so in the vast majority of computational neuroscience, we're using these disembodied models, right? These are models that just sit there and the researcher picks the training data and kind of spoon feeds this data to these models, but the models have no decisions about, given their current knowledge state, I'm going to pick this information versus that information to learn from, which of course animals are able to do. And so I think we need to distinguish between naturalism on the stimuli side of things and naturalism on the embodied side of things. So even though we have really simple environments, right, just a kind of a rectangular room with a single virtual object, the animals can move around that entire space and produce, thousands and thousands of unique images of just that single virtual object. And so I think that kind of naturalism in terms of embodiment is actually quite important and might, we don't know, but might be more important than the naturalism of actual stimuli that you're seeing. So this, of course, is an empirical question like they all are, but, this is what we hope to address when we go to the kind of the more advanced 4-screen VR chambers where we can, really raise animals in a farm or in a forest and give them all the same kinds of visual stimuli you'd actually get in the real world and, see how much that matters versus, you could put a chick in a world and maybe the world doesn't update as it should, right? They move and the world updates a second later, or they move and the viewpoints that you get are radically different than what you should actually get if you're moving in that way, right? So these are ways where we can actually see whether the naturalism of how you move through the world is also causally related to this capacity of learning. So again, I think there's really two types of naturalism that come into play, especially when you start to embrace embodiment in the way that we are.
Okay. So we've talked a little bit about the convolutional neural network experiments, and then it seems like you're just gradually building up and up and up and making it more complex and asking bigger questions. So pixels to action and pixels to actions or action and collective behavior and imprinting with the reinforcement learning agents. That was a mouthful that I just said. But so these are experiments that you've done with, I guess, embodied AI agents, trying to figure out what leads, like what are the criteria that lead to collective chick behavior. And mixed in with that is imprinting story as well. So can you describe a little bit about what led you to do those experiments and what you found there?
Yes, absolutely. So a lot of that work was an attempt to take kind of the beautiful closed loop systems that had been worked out with the ventral visual system, right? I just fell in love with that idea that you could build an image computable model that could be directly compared with a primate or with a human to try to take that idea of building a closed loop system between biological and artificial systems, but extend it to embodiment. So, and collective behavior was one of the first areas we really wanted to target. I remember in graduate school just falling in love with collective behavior. So just, it's quite amazing to see whether it's schooling fish or flocking birds, how they can fly in these amazingly intricate patterns and never crash into one another, and yet end up building these just kind of beautiful dynamic displays. And, I certainly wasn't the first one to be amazed by this, right? So, you can find quotes from biologists 100 years ago where their leading theories were like, maybe animals have some sort of telepathy that we don't have. And that's what allows them to engage in this collective behavior, right? That was our leading theory, was telepathy. And so, and then, in the past around the 1980s, work by Craig Reynolds, he actually created these systems called Boids, which he used it for computer animation. He was an animator and he didn't want to animate every single bird in a flock. So he essentially created these hard-coded systems that with just 3 simple interaction rules, like stay close to your neighbor, don't crash into them, and align your body with them. What he found, and this is also work by Ian Kuzin, who's a biologist, basically they found that these Boids were actually really good models of predicting how they could actually reproduce the kinds of behaviors that you end up seeing animal groups doing. And so this was really neat, right? Because now we actually had a model that didn't have telepathy in it, right? It actually had understandable, hard-coded rules, and that would actually produce the same kind of behavior as animals. But it does leave open this question, right, of where do those rules come from, right? So maybe evolution hard codes in rules, however it might do so, into an animal, because of course being in a group is safer than not being in a group. There'd be a lot of survival benefits to being in a group. And so one might imagine a more nativist story, which is that collective behavior emerges from these hard-coded interaction rules. We thought it might be something different, which is maybe these hard-coded interaction rules come from something more basic, right? Something more core. And so we just tried CNNs with reinforcement learning, just on kind of like on a whim, to see if that would be enough, if that's all you need, so to speak, to use computer vision speak, are those the only ingredients you need to make collective behavior tick? And what we found is that it is. So you essentially, for people who haven't read this paper, essentially you can just take a group of artificial animals and you can give them reinforcement learning and a CNN as an encoder. It doesn't matter how big the encoder is. It can be 2 layers or 3 layers or 15 layers. You basically get the same performance.
Right, that's right.
But you get a sense of curiosity. So it's basically just given 2 different observations, predict what action is going to happen next, predict what the next action is, and then you use the error of the reward in order to motivate the policy network. And as it turns out, that's all you need. You end up seeing groups of animals spontaneously grouping together and imprinting to one another, so to speak, just from those simple ingredients of reinforcement learning and curiosity, and critically being raised together. So this is one thing I really love about that paper, is that you can do controlled rearing experiments on machines the same way you can do it on animals, and then you can causally explore the role of experience in the development of machine intelligence. And so in one experiment, we raised the machines together. So, just like newborn animals, they typically are, there's almost like a litter of animals. And so the first thing an animal sees when they open their eyes are their brothers and sisters sitting around them, right? So, and their brothers and sisters are moving around in unpredictable ways. So you would expect a curious agent to start paying attention to those unpredictable things happening in their environment. You don't need hard-coded knowledge of agents or social groups or anything like that. You just need a curious learning agent to be born with other agents, and they'll learn from one another. If you take exactly those same agents and you raise them separately, no collective behavior whatsoever. So it's not just that RL and curiosity automatically leads to collective behavior. It's really an emergent property of those learning algorithms interacting with these social experiences that rapidly produces collective behavior. And this might be one of your next questions, like, what does this tell us? And I think what this tells us is it gives us an image computable model of collective behavior, right? It tells us the sufficient conditions, the sufficient algorithms and experiences you need to explain why animals group. And there might be lots of models that do it. So this is but this is at least one set of models that actually ends up just producing this without any hard-coded knowledge about, again, agents or social groups or all these other things that researchers have proposed might be innate to explain social grouping.
Can we just talk about the curiosity for a moment, algorithmically? So I think that you mentioned this, and I don't know. I know you tested like a few different versions of a curiosity algorithm, I think. But basically, from what I understand, at least from one line of curiosity-driven reinforcement learning, and I think you just said this, is that you make a prediction, and the bigger the error in your prediction, the bigger the reward. And then you update the policy based on how big that error was, and then you take actions to explore that space more and make more predictions. Is that right?
Exactly.
Okay.
Exactly.
Is that okay? It's an odd. I mean, I think that if you only did that would lead you astray in real life. But there must be some sort of reward function. I mean, the idea is that it's like an intrinsic reward without an extrinsic reward.
That's correct. And I should mention this algorithm came from Pathic back in 2017. So Pathic. I just, full credit to him and the Berkeley group that came up with that. We were just excited to have an unsupervised system that could actually learn in an environment.
You're just waiting. You're just waiting for all these tools to hit your lab, right?
Exactly. That was one of the ones we were waiting on. So yeah, that's absolutely right. One critical thing that might kind of help explain or make sense of how pursuing novelty could lead to something like familiarity, right? There seems to be like a tension there, is you need a critical period. So this is, you have to subject the machine to a critical period so that you ramp down learning until eventually learning is at zero, the same way that in an actual animal, we see critical periods all over the place, especially in imprinting, is initially chicks have their imprinting period open for about 3 days, and then it shuts down. And so if you don't put the machine through the critical period, it'll just continue to explore novelty. It's really about shutting down that learning with a critical period that allows us to match animals and machines. And my hope is this tells maybe AI researchers something important about critical periods, right? So this is almost non-existent in the AI or ML world. It's basically you just take a huge amount of data and you train these large-scale systems, but maybe there's something really important about learning something and then having a critical or sensitive period and shutting it down and having that serve as the foundation for the next stage of learning. We know the critical and sensitive periods are widespread in animal brains. And so, my hope, or what our lab is doing, is to essentially start using critical periods in machine learning studies and see what this might buy us in terms of being able to match the behavior of animals and machines. And at least in collective behavior, it seems to be essential.
So thinking about humans, at least these days, a lot of people spend a good deal of effort trying to practice beginner's mindset and for that critical period of curiosity and novel seeking to never end. And we do it in various, artificial ways, for a healthy mind. But I suppose this is how, our own critical window is how we become prejudice and how we stop learning new things. And I mean, should we fight against that or should we embrace it as humans,
Right. I think that's really great. Yeah. There's this phenomenon called the baby duck syndrome in human computer interaction, which is that people tend to like the first computer systems that they ever used. And then they have a hard time adjusting to other computer systems, right? So in a way, that's like we're imprinting to our computer system because we're learning habits and policies that allow us to use that computer system really well. Then when you switch to another computer system, now you need to kind of relearn a bunch of stuff. So I think we see this kind of widespread across human behavior if you pay attention, right? Children like watching the same movies over and over and over again. And we really like familiarity. And, there's even I can't remember the reference, but I remember this paper came out, it was in Science, suggesting what is the top cited papers. And the top cited papers are often papers that are 90% familiar and 10% novel. So, we really don't like pure novelty. We want a lot of familiarity to kind of ground our foundations of knowledge, and just a little bit of novelty added on top ends up producing kind of the most impactful scientific paper. So, I think you can often think that humans are just curiosity machines, right? We're constantly going out and seeking new experiences and acquiring data, but that's not actually how it works, right? I mean, we do that sometimes when all our other needs are met. But I think it's actually, if you look at 24/7 behavior of an animal or of a child or of a human, you see something really different.
Yeah. Yeah, walked in on my mom this morning. So I'm visiting family, and she's just on her iPad playing solitaire like she does every morning. It's like, oh, come on, Mom, do something new, explore some new space. I want to ask you, maybe I'll come back to imprinting later, because I want to ask you about like what the current science of that is. And I know this is another aside, but so thinking about these reinforcement learning agents and just raising the chicks in these environments, and maybe especially the first studies that we talked about where, there's this funny looking object that you're testing them on in this controlled rearing experiments, and thinking about development and critical periods. Do we have any idea what this does to their visual cognition as adults, if you're training them in these environments, and how you might guess, with artificial agents, if you could study that as well?
We don't know yet. It's a really good question. Right now, we don't. This might be another waiting period because we don't have the same kind of continual learning systems that we know that biological systems can do. So right now, we've just been focusing on the very first, or just the very first few objects that newborn chicks create. But our hope is that as continual learning kind of ramps up in the machine learning world, then you could imagine raising chicks until adulthood. And we actually have these chambers ready to go where you could actually, give an animal one set of experiences for the first couple of weeks of life, and then a totally different set of experiences the second few weeks of life, and ask, how does that does that animal then end up navigating those different learning landscapes in order to adjust? And then, of course, you could put the machine in through exactly the same ropes, right? You could ask, does that machine end up relearning in the same way that the actual animal ends up relearning? And I think this will be helpful because there might be a lot of ways to build a continual learning system, but we'll have no way of knowing which is right or which is wrong as it compares to animals unless we actually put them in a closed loop system with one another. Right? We have to raise them in the same worlds. We have to test them with the same tasks. If we're not doing both of those things, we'll never be able to say whether they're the same or different in terms of how they developed. So the kind of, again, coming back to the general theme is, I think we need a test bed that is publicly accessible, where we have rigorous data of animals and machines being raised in the same worlds and tested with the same tasks. Once we have that, we can come up with whatever tasks we want or whatever we care about, whatever the next stage of AI evolution is. And then we just test the animals in it, and then we just plug those same sort of algorithms into the machine and see what works and see what doesn't, what closes the gap, and then we move on to the next problem.
So this is really exposing my naivete, but there must be other people who are using AI models to study development that are not doing it in a controlled rearing from birth setting. I'm not going to. I don't want to ask you like what you think of that. If that's all for naught. But I mean, maybe what does that world think of the controlled rearing aspects, or what is there value still in doing something that is not as perfect as your research is?
Absolutely. So, the first thing I would say is that I could really care less about chickens, right? So that the reason I use them is because they're a model system that allows us to discover general principles of how experience and core learning algorithms, whatever those are, interact with one another. But I don't think anybody in the field will be convinced if we just discover something with chickens and it doesn't actually generalize to any other species. So, ideally, chicks are a way we can actually make a deep run at these questions. I think I mentioned the study where you can, raise an animal where object permanence is false. This is something that we recently did in case you want to chat about it. But, that's something you could never do with a baby, ethically or practically. And so the hope would be that some of these general principles we discover from chicks could then be applied to humans, for example. And, Brendan Lake is doing some really wonderful stuff in this regard. So he takes, for example, SACAM data that Mike Frank put together along with a bunch of his collaborators and essentially trains transformers and CNNs through the eyes of this baby cam data. And, that's great because it's the same approach. You can't vary the visual diet of a baby the same way that you can with a chick. But if what we discover with chicks is right, we should find that same approach should work with babies too, right? It's going to be just much more complex experience. You won't be able to figure out how particular experiences really impact the development of vision, but it's a critical sanity check to make sure that whatever we're discovering with chicks actually does apply to animals more generally. So I think we need to use lots of model systems. I think that just sticking with chicks would be a mistake. So we actually even do stuff with fish. So for collective behavior, we have a fish collective behavior paper where we find that if you insert, you can basically look at the emergence of collective behavior in fish, and it takes about 21 days for them to start to group together. So we built a bunch of virtual fish and put them in virtual fish tanks. And what we found is that the development of collective behavior is identical across those virtual fish and the real fish. So they start not caring about one another, and then they gradually start grouping together more and more during development. And you can see this kind of parallel developmental trajectory across the biological and artificial systems. And so, again, I think it's really important to use different model systems and really try to discover general principles of learning rather than just specific things that might happen in an individual animal.
I know that we're all over the place here, but I'm just curious. So there's a difference between collective behavior and swarm behavior. Is swarm behavior a type of collective behavior? Or, subtype? Okay.
That's right. Okay. Exactly. So collective behavior just generally refers to animals interacting with one another, and they can form a lot of different kinds of dynamic systems, so to speak. Swarming is a particular kind of collective behavior that emerges when certain characteristics are met.
So you're not studying chick swarming, which would be something else. But I also, like you'd mentioned the object invariant, breaking those rules, raising them in conditions where object invariance isn't a thing. So tell me about that, and then we'll come back to the reinforcement learning again. I know it's terrible that we're jumping around. Sorry.
Oh no, that's okay. That's okay. No, this is one of my favorite experiments, so I'm excited to tell you about it. So this has no AI or ML component
Okay.
yet. We really hope it will. But the study is basically, imagine being raised in a world in which object permanence is never true, right? So here's how the experiment works: is you again take a chick, you hatch it in darkness, you move it over to a video game, basically a video game world that's where the chick controls the actions happening in the video game world. And then for the first several days of life, the chick sees like two screens. So there's an object, two screens move up, and then the object goes behind one of those screens, and then the screens move down.
Uh-huh.
Now, in a natural world, the object's always where it was when it disappeared or when it moved out of view. Whereas in the unnatural world, the object's always behind the other screen, right? As if the object teleported from behind one screen to the other screen. So we raise chicks either in the natural world for several days or in the unnatural world for several days. I'll just point out, of course, that only the chicks in the natural world had experience that object permanence was true, right? The chicks in the other world had the opposite experience. If it's pure learning, they should have learned something radically different than the chicks raised in the natural world. As it turns out, they look exactly identical to one another. Their behavior is almost identical, with both the natural raised chicks and the unnatural raised chicks both showing object permanence. I love this study because it shows why we need VR, right? So one could have guessed, and this is, many empiricists think this, is that object permanence is learned, right? You have ample experience seeing objects, balls rolling under couches and then reemerging, or dogs going away and then coming back, right? We see this all the time. And so maybe object permanence is learned. The only way we could ever figure that out is if we actually put animals in a world where object permanence wasn't true, where you didn't have the experiences you needed to learn that. And then you can ask, does the animal still show that capacity? And for the case of object permanence, we still do see that. So our speculation is that prenatal training data is so rich that maybe it builds a visual system that has object permanence in a sense baked into it, so that even when you get contrary experience, that initial foundation is so strong that you just can't unlearn it. And given that a retinal wave is a lot like an object that's obeying object permanence as it moves across the eyeball, basically from the moment the brain is growing, or from the moment the retina develops at least, you're getting experience that object permanence is true during prenatal development. And so, I love this way of basically being able to look at what's learned and what's not learned through VR, because it lets us make a clear distinction. We know in that case that it's going to be some sort of nativist story in terms of where object permanence comes from.
Okay. I'll finally bring us back to the deep reinforcement learning, collective behavior stuff. And one of the interesting things is, so with the convolutional neural networks, the experiments we opened up with, it seems to be more. The inductive biases are inbuilt essentially, and you talked about this domain general learning knowledge, and it takes very little for them to learn the object permanence, object invariance. But you make the point that in terms of the collective behavior, you actually really need that curiosity-driven learning algorithm. So it's really a learning, more of a learning story in terms of collective behavior than it is in terms of visual cognition. Basic visual cognition, I guess.
Yeah, that's right. So if I don't answer your question directly, feel free kind of to ask it again. So I think kind of what you're suggesting is maybe there's a little bit of a tension between the CNN results and like the collective behavior results.
Well, it was kind of an open-ended question, because I don't. That's just from my perspective. It seems like that there might be a tension, but could be an easy story to be made that, they're both at play, because we're nativists and empiricists, and they're both right, I suppose.
Yeah, at least that's my view. So I'm glad you asked. So right. So with the CNN results, what we find is that if you use a supervised linear classifier, you can read out from a frozen CNN view invariant object features. And you can discover those features in the embedding space using even just a single viewpoint. So even though it's supervised learning, which the chicks don't get, you can still use a very small amount of data in order to find the right set of features in the embedding space that allows for view invariant recognition. Now, that works. So that suggests that the CNN is at least developing the features it needs or learning the features that it needs in order to be able to succeed in the task. But that's quite different from an embodied agent discovering those features on their own. Right. So in one of the papers I sent you, we call it a newborn embodied Turing test. So this is an experiment that's really similar to collective behavior, but essentially we take exactly the same agent, except it's just one little artificial chicken in a chamber instead of a whole group of them. This matches directly to the virtual, to that experiments with the chicks. And what we find is that even though our CNN experiments show that view invariant recognition can be learned from this sparse data, we find that the embodied agents don't discover those features. So in fact, the machines end up looking radically different from the actual chicks. So the machines develop view-dependent representations rather than view-invariant representations, right? They're really kind of, it's almost like they're relying too much on statistical learning, or they're fitting to the data a little bit too much. We also found, this is work by Manju Garamella in our lab, she finds that machines are very background dependent. So this was an experiment where we raised, one object on one background. So that was their entirety of their visual experience for the first week of life. So if you're relying purely on statistical learning, you should yoke the features of the object with the features of the background, which is what you don't want, because then you can't recognize that object across novel views. Well, chicks are wonderful at this. They're not at all thrown off when you change the background, but machines are terrible at this. So you change the background on a machine, and now they go more by the background than they do by the object itself. So this suggests that even though we can get these systems to imprint in the same kinds of chambers where we get real chicks to imprint, what we're not finding is the same kind of recognition capacities developing. So this leads us to think that there's something missing. We have no idea what that is. We have some guesses, of course, but there must be something missing in the machines that the animals have that allows the animals to develop these view invariant, background invariant representations that really support high level vision. So that's what we currently see as kind of one of the big things in the lab is how do we get an embodied agent to discover that particular set of features, the high level features that are needed in order to solve the task.
You said,
and that could be. Oh, sorry.
I was going to say you said you had some guesses. I think you were about to say some of your guesses, perhaps.
So one of our guesses is the retina is highly dynamic. So, right, in machine learning world, we often feed in RGB images.
Right.
But if you look at what data looks like, visual data looks like after it goes past the eyeball, right, after it goes through LGN, it just looks completely different. You only essentially maintain moving features. And so there's these wonderful demos called the dynamic visual system. Demos that people can pull up. I'd highly encourage you to do this, where you can convert a real video into a DVS video, and you can see that basically, you get rid of 99% of the data, but the only thing left is what changed.
Right. Okay.
Right? Because you're only keeping those changing signals, which is what neurons do. And so that might solve the problem, right? So it might be the case that if you're only paying attention to moving things, and we have some data suggesting that this is what chicks actually do, if you're only paying attention to moving things, you've made your computational problem a lot easier. Rather than having to reason over the whole 224 by 224 image space, now you just get to worry about those moving features, and those moving features will then be automatically segmented from the background, because if you still your head, the background's not moving, but the object might still be. Yeah. And so this is one way that a biological system, just based on having a different eyeball, right, having a different body, not having a different brain, but having a different body, could lead to radically different kinds of changes. So, kind of more generally, I hope what happens is that rather than just focusing on the learning algorithms per se, is I hope the field embraces morphology as well, because it might very well turn out that the body of an animal, right, like the nature of their eyeball, the nature of their ears, the nature of how they move through space is going to influence their training data. It's going to influence what they perceive. And I think we're going to have to start playing around with different artificial bodies, the same way we've been playing around with different artificial brains in order to have a chance of closing this gap between animals and machines. So that's my speculation. I think it's really about the eyeball per se and the nature of the input you actually have going into the visual system, rather than just the RGB frames that we typically feed in now.
That's sort of a bottom-up attention story, right? That if you're attending to relations or actions or differences in movements, is there a top-down story in chicks also?
I just, it depends on what you mean by top down. So I tend to,
Yeah.
my world was rocked by Henry Yen a few years ago when he came on your podcast and he started talking about negative feedback control systems, which really kind of question what
Yeah.
it even
Yeah.
means to be bottom up versus top down. So,
Right.
ultimately, I think what you need to do to test that question is just kind of build in whatever you mean by top down, instantiate it into the brain of the artificial animal itself, and see if that ends up making a difference, right? So you might imagine that if an animal is trying to control some internal homeostatic variables in a negative feedback control system, then that might influence the kinds of features that it's going to end up paying attention to depending on its current needs, right? So if you're
Yeah.
hungry, you might pay attention to this set of features, and if you're thirsty, you might pay attention to this set of features, and if you're scared and being chased by a predator, you'll of course look for a third set of features. So I really think that the embracing the control of a system rather than the kind of input-output approach that we've been taking in ML and AI might turn out to be quite important, especially as we scale from these disembodied systems to the embodied systems that actually act in the world and have goals of their own in some ways.
Yeah. Yeah. Those internal set points. You mentioned, Henry Yen.
Yeah.
Like, what are those internal set points? Is it all homeostasis? Like, where does it all derive from? It's really hard and fascinating to think about for me. There's this paper by Michael Anderson, whom I've had on the podcast, and it's all about like behavior as what they call, and Vicente Raja is the co-author, what they call behavior as an enabling constraint. And, as you were thinking, right after I said, well, that's kind of a bottom-up attention mechanism, the other thing with morphology and the way that our eyes work and the way that we interact with the world is you could kind of think of that as a top-down constraint as well, because it is like top-down, did I say constraint? Yeah, mechanism, constraint, whatever, because it is constraining the way the signals that get in and how they get in. So that's almost a top-down thing. And you were saying, well, it depends on what you consider bottom up and top down, and it all gets mixed up, I suppose. But do you think of the environment and our behaviors? Do you think of that as shaping our neural activity in a sort of top down constraining kind of way? Also,
absolutely. I think that the way of looking at the way of building scientific models by allowing those models to do tasks in their own right and then putting constraints on those models to see if we can push them to the same part of the parameter space as biological systems, I think that's absolutely the right idea, right? So this, of course, comes from, Yeamans and DiCarlo and, Pico Scort and a bunch of other wonderful people. But I think we'll need to do the same thing with embodiment, right? So your body places constraints on what you can see and what you can do and what kind of training data you can acquire. Your physiological needs are going to place additional constraints on the kinds of things that you look for in the world. Even the nature of, as we were talking about, the nature of your eyeball is going to place these radical constraints on the nature of the data actually going into your brain. And so I think all of these, we don't know which constraints matter and which don't, right? That's why we're doing the science in the first place, is to figure out what matters and what doesn't. Right? We have, thousands and thousands of details of phenomenon and lists of facts in neuroscience, and we don't know what matters and what doesn't. And so I really love this reverse engineering approach because it gives us a way of figuring out at that engineering level of abstraction, what do we need to keep and what can we throw away in order to be able to build functioning intelligence. And so I think that, we should just add constraints and see if they matter. Some might matter a huge amount, some might not matter at all. But we can do this, we can take an empirical approach on this and just, plug them into the artificial animals and see which of those constraints really matter and which don't. But yeah, I think that's how we get a domain general system being pushed to the same part of the parameter space as an animal, is through heavy, heavy constraints on their morphology, on the learning rules, on the architecture, on all the various things that have been pointed out by some of your prior guests.
How far can you push your system, your pixels to actions? Like what's your vision for how far you can take this and where the limit is? Do you see a limit?
Wow, it's a great question. I hope this doesn't come off weird, but I don't see a limit. So the reason I tried to do this 10 to 15 years ago was because I wanted to fully embrace an entire whole animal, right? So like a chick does, it does every, it recognizes objects, it navigates the world, it develops social connections, it solves all of the problems that animals solve. And so, I don't want to say anything negative about the kind of piecemeal attempt that we've been attempting in the field where we'll try to reverse.
You need them all, right?
Right? You need them all. Yeah, right. Yeah. I mean, and the beautiful work of, the visual system and the auditory system and the olfactory system, I mean, that's absolutely wonderful work. But at some point, we're going to have to put those together into a single unified system and then see if that single unified system develops a visual system and an auditory system and all the various kinds of systems we actually see in a real developing organism. So I think we have to take development seriously, because the only evidence we have of an intelligent system is through development. Typically, we'll take an adult state and that will be our target, and then we'll try to build an ANN through massive training. We won't care if it's evolution or development. We'll just say, it doesn't really matter, but we'll just take that ANN model and compare it to an adult animal.
Right.
And I think that's fine, depending on what your goals are. But if you want to build a unified model of intelligence, you have to take development seriously, you have to take embodiment seriously, and you have to take agency seriously, right? You have to let just like real animals who are embodied and can decide what they're going to do next, you need to give machines that same kind of capacity, because ultimately, I think the name of the game is to ask how much of the phenomenon can you explain through your model. And if we get it right, I imagine it'll be more complicated than this, but let's just say that it's a transformer, right? So if we stick a transformer into a developing chicken embryo, artificial chicken embryo, we give it prenatal training data and all that, and then we give that artificial chicken the same kinds of experience as a real chicken, and it starts to develop object recognition, and it navigates path integration and snapshot-based navigation and reorientation and all the core capacities that nativists have pointed out over the years. If we find that one model doing all of those things, we've now then got a unified model, a unified closed loop system model that can be used to then do additional tests. And so that to me is kind of at least what our lab is chasing, right? We, like the same way that Darwin gave us DNA as a way to connect tigers and worms and insects to one another through a common medium. We need something like that for psychology, right? We need some sort of medium. Maybe this will be like a transformer or something else that allows us to explain why brains develop object recognition and smell and navigation and decision making and face selection and all the various things that we develop, right? But I think that we need to embrace or chase a unified model, and this is the only way I can see us doing it is taking development seriously and controlling data from the very beginning of life.
Surely the transformer is not it. Surely the transformer is just another 5-year thing that will be replaced. Yeah. You mentioned you keep mentioning transformer because that's like the latest and greatest, right? And
it's the latest and greatest, and it's definitely push back on me if you don't agree, but it's in many ways, I consider it to be one of the best models we have in cognitive science. I know it's not treated that way, of course, but it's the one model we have that can do a bunch of different things. So there's this beautiful, Gatto model from DeepMind, for example, that can can play video games, and it can caption images, and it can write essays for you, and it can control a robot arm. Right? This is one of the first examples we've seen of a single unified system that can actually do a wide range of different things. And given that that's the only system that we have, and given that that's one of the hallmarks of human and animal intelligence, I really think that we should treat transformers seriously. We don't understand how they work yet, but that's okay. We didn't understand how steam engines worked until we built it and then reverse engineered it. So I think we want to just first find a system that can do all of these different things, and then we can make sure it actually matches the biological system, which is what we're trying to do. And then, of course, all the brilliant mathematicians of the world can try to understand how these things are working in a way that gives us a feeling of understanding, whatever understanding means. I think it's going to mean something different to everybody else.
I mean, it seems like your lab's going gangbusters, and like I think I mentioned this earlier, just you probably have 15 different experiments, ideas, things to test lined up. What's give me just a quick flavor of what to expect over the next year or something from your lab. What's in the very beginning stages now that you're, and then we'll wrap up, I promise.
Oh no, this is really fun. Next stage will be, hopefully we'll have every chick experiment we've ever done publicly available for people to try. So this will be hundreds of experiments. So instead of just the 1 or 2 experiments we talked about here, it'll be hundreds of experiments with detailed data from chicks. people can basically plug in their model and test it across the whole test bed. And then that way we have this integrative benchmarking approach, focusing on this, I think, fascinating question of the origins of knowledge. So that's what we hope to have that up and running in the next year. And then the other thing will be, we're going to be start exploring other capacities. So I've always loved navigation, especially because a lot of core navigation abilities emerge quite early on, right? So you see newborn animals doing things like path integration and snapshot-based memory and reorientation. This is, part of kind of the core knowledge tradition. And so I'd love to see, what does it take? What kind of learning algorithms do you need in order to reproduce core navigation in a machine? And we can play the same game of raise the machine in the same world as the animal, make sure that they get the same training data. And then we can start asking, again, does that same core learning algorithm that gives us object perception, does that very same algorithm also give us navigation? And then in the future, does it also give us social cognition, right? So can we slowly expand out the range of tasks until we have a single unified model explaining all the various things we care about?
That is the dream.
That's
okay,
the dream,
folks.
Yeah.
I have nativist Justin Wood. No, I'm just kidding. I have non-nativist nor empiricist, but accepting of both. Justin Wood. Hey, Justin, I'm glad that we finally got to connect. We had to keep kicking it down the road, but I appreciate you coming on. And of course, best of luck, even though you don't need it. And thanks for being on.
Oh, thank you so much for having me. It's been a pleasure.
I alone produce Brain Inspired. If you value this podcast, consider supporting it through Patreon to access full versions of all the episodes and to join our Discord community. Or if you want to learn more about the intersection of neuroscience and AI, consider signing up for my online course, Neuro AI, The Quest to Explain Intelligence. Go to braininspired.co to learn more. To get in touch with me, email paul@braininspired.co. You're hearing music by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.